Hello everyone and welcome. You're watching the Promess Christmas Smash It Special. I'm Gibson Kramer.
And I'm Peter Parsons, and we've got a lot of fun demos for you to see today.
Some of those include lighting a candle. We're also going to be cracking a nut with the nutcrackers, so make sure you stay tuned for that. We will be doing a question and answers at the end of this, so if you do have any questions, feel free to throw those into the chat. Also, if you have any suggestions on future things you would like to see smashed, add those suggestions to the chat as well. Thank you very much and enjoy the video. Welcome everybody. We're in the Process Development Center here at Promess. You're watching the Christmas Smash It Special. Tell the people what we're going to be doing today, Peter.
All right, I'll tell you, Gibson. So today we're going to be smashing a snow globe. And so this is a size 2 workstation, and we're going to be coming down at this full force, full speed. How about you shake that up for me, Gibson?
All right, yep. Couple good shakes. Here we go. All right, for safety.
Let's let her rip.
Oh my goodness. All right, how much force did we see?
We saw a max force of about 4 kilonewton.
Okay, apparently not very much to smash a snow globe. Awesome, that went really well. Thanks for watching and stay tuned for the next segments.
We're here in Building 2 in our development center. Here to show you our gantry workstation. Now our gantry workstation is comprised of an X and Y axis gantry, on top of which is one of our 12 kilonewton presses, which is about 2,700 pounds. And we're going to be lighting a candle and then smashing it. Gibson?
Yep. So using the software, I've programmed all 3 axes here. We're going to start by coming down and striking the match, and then we're going to move up and light the candle, and then we're going to smash it. So let's go ahead and get this started, Peter.
All right.
Go. Oh yeah.
Wow.
That was beautiful. Fantastic. All right. Now let's go ahead and take a look at the data we captured from that. Looking at our screen here, we can see a large peak right in the beginning. It looks like we're just shy of 6 kilonewtons. And then as you saw, the candle crumbled underneath it and the force fell off. And then as we got closer to the base plate, it started growing back up to our 11.5 threshold. So really happy with that. It looked sweet and I hope you guys enjoyed it too. Let's go ahead and move on to our next segment.
We're here at the Process Development Center, working with a size 1 workstation. And today, we're going to be squirting some icing onto an external load shell to show you the capabilities. Behind the plastic here is an external S-beam load cell with a large plate on it. And here, we have a plunger full of icing. This press is going to come down and evacuate this cylinder, and hopefully, all that frosting should go right onto that plate. And we'll see what kind of forces that provides us with.
All right, let's do this. Aimed up.
All right.
All right, I think we're ready to go. Hopefully that video still looks cool. And looks like we still did get some frosting into the load cell. So let's go ahead and look at the data. All right, we can see here we're looking at our S-beam load cell. So we do get a spike in force, pretty small overall. What do we see on the ram here? Go ahead and zoom to extend. So we got up to about 600 newtons before we completely bent the rod on the plunger. So it wasn't exactly what we expected, but I hope you guys still enjoyed seeing this little test of ours. Thank you very much.
Merry Christmas, Gibson, from me to you.
Oh, fantastic, Peter. What could it be? Let me open her up here. What is this? A gingerbread house? Let's go make this thing.
All right.
Ooh-wee. That was fun, Peter.
Oh yeah.
What should we do with it now?
We do have a size 3 workstation right behind us.
Oh, yeah, we do. You think we should smash this thing?
I think we should smash it.
All right, let's smash it. Get her loaded up here. You said this was our size 3?
Our size 3 workstation.
All
so
right.
we're going to be coming down on this gingerbread house, reindeer barn, and we're going to smash it.
Let's do this. Oh, the anticipation. Oh, yeah. Crunchy. Nice, all right. Let's see what kind of force we got here. As we can see here, we pressed all the way up to 60 kilonewtons. Actually, crushing the gingerbread house only resulted in about 1.1 kilonewtons. We can see there. Very small blips on the whole grand scheme of things here. So what we learned is gingerbread houses are pretty fragile. Be careful this year whenever handling your gingerbread house.
We're here in Building 3 in our final assembly area, and we have a couple of benchtop workstations here. Now there's 3 different configurations here, but the one we'd like to focus on today is our L-frame benchtop workstation. As you can see, there are a couple differences that it has, but one of the main ones is that there's no enclosure built around it, allowing different sized parts, such as long ones, to be pressed without the need of a restrictive enclosure around it. Additionally, the safety also differs. These other 2 have light curtains on them, but instead, this one has a 2-hand tie-down, meaning that the operator needs to put both of their hands on the 2-handed tie-down during the entirety of the press. This ensures that the hands are kept in a safe location.
Here at Promess, we try to simplify our processes as much as possible. Today, we're going to flip that on its head. We're assembling a strand of Christmas lights that had a broken bulb. We're going to use our L-frame benchtop here to insert this bulb into the strand. This is probably the most convoluted way you could possibly do this, but let's do it, Peter.
All right. 1, 2, 3.
Fantastic. And there you can see, using this L-frame, you can assemble any strand of Christmas lights you need. I'll take a quick look here. It looks like we got up to about 124 newtons, so not very much force to repair the strand of Christmas lights. I hope you guys learned something today, whether it's about Christmas lights or the L-frame. Thank you very much for watching. Stay tuned for our next one. Hello folks, we're in front of our size 2 workstation here. What are we going to be doing, Peter?
Well, most of what you've seen so far has been compression on these presses. So what we'd like to show you next is one of the tension capabilities. So here, with our size 2 workstation, we have the RAM all the way extended, and here we got some tangled up Christmas lights here. Now, instead of going through, untangling by hand, we're going to use our press to do it. So we're going to pull up, and we're going to see what happens.
Let's do it. Getting taut, starting to crack. Finally lost the lights. All right. Looks like they came apart pretty well there, Peter. Let's go ahead and take a look at the data. Let's look at our force versus time curve here. So it looks like, again, as we're pulling, we're going to have a negative value. And these big drops here, where we're actually increasing, looks like these are where each individual one of those strands had broke. So we can actually see where all these individual strands were snapping rather than just one big break. Look, this was a big one. This was holding a lot of force here, and then it broke, and then it released a lot of that negative tensile force that we have. And there we go. The tensile force of a light strand here. We do have a max here. It looks like we reached about negative 1.6 kilonewtons. Hope that was informative and interesting for you guys to watch, and thank you very much.
We're here at our Process Development Center, and here we're looking at a 3 kilonewton 4-post benchtop workstation. And we're going to be smashing some ornaments.
We picked up some ornaments. They say shatterproof on the package, so we're going to test that. Put that in here. Start our cycle here. We are just driving down to a position, so here we go. All right, it looks like it's stuck to the end of the ram.
But I didn't see a shatter, did you, Gibson?
Definitely no shatter. I think I did hear a little bit of cracking, but it's all in one piece. Well, we're not here just to compress stuff. We want to break some stuff today.
Yes, sir. You're going to see an ornament shatter. So here we've got a glass one, nice and fancy. We'll see how this one fares.
Let's do it. All right, fantastic. Definitely a lot more dramatic than the plastic one. And now we're going to take a look at our graphs here. We can see the glass one is what we're looking at first since it updated. We see one big spike right in the middle here, and then the force dies off as the bulb shatters away. If we go back to the plastic one, here we can see the force is pretty steadily building right up to the peak here. So kind of what we would expect from the different materials. Thank you for watching, and tune in for our next segment.
We're back in our Process Development Center at our Size 2 workstation. And next up, we're going to be cracking a peanut.
Yes, we are. So I've programmed this press using a rate of change formula. This will be coming down and cracking the nut, so looking for a drop-off in force. And once it sees that, it will return before it smashes the nut entirely. So let's get it loaded up. I will start the cycle. Fantastic. And as you can see there, we just cracked it, but we didn't smash it entirely. Let's look at some data. All right, looking at our force and position graph first here, it looks like we got up to about 0.08, 0.09 kilonewtons. And then again, we saw that steep drop off in force. Again, if we look at our rate of change graph, this big drop off in force is what we were looking for there. And once we found it, we retracted, so we were no longer squishing on the peanut. All right. Peter?
Well, next, I think we should try cracking a peanut with a nutcracker.
Brilliant idea. All right, here we go. Let's see if we can smash that nut. And let's look for it here. Looks like it completely flew out of his mouth.
I think I found the peanut.
Is it cracked?
Doesn't look like it. Here at Promess, we believe in second chances, so we're going to try to go it again with this nutcracker. See if we can crack that nut.
Let's do it. There we go. I'd say that was a success. This is our nut here, properly cracked this time. Nutcracker won. All right, let's take a look at the data. All right, looking at the graph here, it looks like we saw a big spike up to about 17.4 kilonewtons to absolutely destroy this nutcracker. I hope you guys liked watching that, and thanks for tuning in.
We hope you enjoyed watching that video. Now we'd like to answer any questions that you have.
Looks like we had a couple questions here. The first one, what is the heaviest force your presses can do? Peter?
I can take that one. So we have a wide range of sizes for our different presses, ranging from as small as 0.2 kilonewtons, or about 50 pounds, all the way up to 500 kilonewtons. But in some situations, we can go even higher for custom solutions, up to almost a megaton of force.
All right, the next question here, how accurate are your force and position measurements? So for the force, our standard is about 1% of the full scale. So if it's a 100 kilonewton system, that would be about plus or minus 1 kilonewton. Now we are able to add external load cells if you do need more accuracy in a specific range. And now for the position, our accuracy on the position is 25 microns and the precision is about plus or minus 5 microns. So pretty tight.
Looks like we've got another question. Can you add other sensors besides a load cell to a Promess system? I think you kind of touched on that a little bit, Gibson.
Yeah, so along with different load cells, we can take in a lot of different types of sensors. We've have specific experience doing different pressure sensors. We've also experimented with some lasers as well. If you have a sensor you would like to incorporate, definitely reach out and talk to us and we can have that discussion with you guys.
Let's see. If we buy a press, can we have Peter come service our system? Well, I'll have to see what I have on my schedule at the time, but we'll see. How much does it cost to use your PDC to prove the force on a project that I'm working on?
That is a fantastic question. The Process Development Center, or the PDC, is free for you guys to use. If you don't know what the force range is for your specific components or process, send your parts in or come in with your parts and work with me or Peter or somebody else on our application engineering team, and we can help you develop a process for your parts and also give you a force range that makes speccing out the system a lot easier. Definitely take advantage of our Process Development Center. All right, it looks like that was the last of the questions. Again, if you do come up with any more questions, you can always reach out to us at sales@promessinc.com, or you can always give us a call at 810-229-9334.
Well, it looks like we got one more question here. Did you have fun smashing things?
That would be a yes. Yeah, it's incredibly fun to kind of play around with these presses a little bit more and move away from specific applications. So we thoroughly enjoyed doing this, and I hope you guys thoroughly enjoyed this as well. Thank you very much for watching.
Have a very happy holiday season.